Okay, we're going to do chapter class 101, chapter 3 test. And the price of a computer increased from $3,999 to $4,500 when the screen was enhanced. Okay, so the difference between these two is 501. And when we figure out the difference, that's the absolute change. So the difference is $501. So we could write the sentence that the computer increased from there when the screen was enhanced. So the enhanced is $501 more than the original. Or you could write it the other way. Either one of these works. The original is $501 less than the enhanced. Okay, so either one of those works. And it's just talking about how much the change was, 500. So you're either going to say one is 500 more than the other, or the other is 501 less than the first one. That's using the absolute change to talk about the difference in price. Now, if we're still talking about the change up here, but want to do percentage, we would say either 501 divided by the 3,999 times 100, which would be 12.5, or we can do 501 divided by the 4500. Now, the sentence that we write, one's 12.5%, one's 11.1%. How you write the sentence that goes with those depends on which one you're doing. Which one was the divisor here? The 3,999 or the 4,500? So, if I did the first one, then we're talking about compared to the 3,000 original. So we would start not with the original. We're going to end the sentence with the original. So we're going to say that the enhanced is 12.5% more than the original. And that's because we divided by the original, so we're comparing it to the original. Now, the other one, we're comparing it to the enhanced. So, the original is 11.1%. 11.1%, if I multiply that by 100, is 11.1% less than the enhanced. We're comparing it to the enhanced price. how much was the change over the enhanced. So the one that's in the denominator of the fraction, $3.99, the original, and we're talking about this percentage is how much this amount is more than that. And then here we're talking about how the 501 is how much less than the 4,500 the original is. So the original is 11.1% less. Again, it's important to look at the denominators. And the same thing when we do the fraction. Now in the fraction, we're just going to take 1 and divide it by the other divided by the 1. So I'm going to do 3,999 divided by 4,500. One answer, 88.9%. The other answer would be 4,500 divided by 3,999. And that's 112.5%, multiplying those by 100. So now when I write the sentence, it's again important which one I'm comparing it to. So the 4,500 is the enhanced. So I would say the original price is 88% of the enhanced. Now instead of saying more or less that we did in both of those, we're going to say of the. So for the first one here, I have the original is 88.86%. Is 88.9%, rounding it off, of the enhanced. Because we're comparing the original to the enhanced. Now, if we do the other one, we're comparing the enhanced to the original. The denominator is original. So the enhanced is 112.5% of the original, because we're comparing it to the original price. How's the enhanced compared to the original? How the original compares to the enhanced depends on which is the numerator, which is the denominator when you do these fraction relationships as percentages. Okay? So we have the same situation down here. Statement comparing the two. So we could either do a fraction comparison or we can do a change comparison. So whichever one you want to choose. I'll just do the fraction one. And we want to, so we have the price of gaming at the local store and at the best deals. So if I do $3.59 divided by $3.29, I'm comparing the price at the local store to the price at best deals. So the local is 109% of the best deals. I could write it that way. If I flip that fraction over, 329 divided by 359, I get, now I'm comparing it, the best deal to the local. So the best deal price is 91.6%. It's less than the local store, so it's 91.6% of the local store. Or we could do it as a change, compare them via change. So the difference between $329 and $359 is $30. So I can either do 30 divided by 329 or 30 divided by 359. So I can say in the first case, I'm comparing the change to the best deal price. And so the change, it's 9.1%. So the local store is 9.1% more than the bottom is the best deal. So that's got to be more than the best deal. So the local price is 9.1% of more than the best deal. Or if I do the division by the other one, then I'm talking about the change compared to the local store. So 8.3%, 8.4% rounded off. And now we're comparing it to the local store, so it's less than. So it's the best deal price is 8.4% less than the local store. So again, when you're looking at percentages, you really got to watch what's it can be compared to, what's in the denominator. Now, you only needed to do one of these, but you got to do one of them correctly. Okay? So we're going to continue with this deal. The price of an app increased by 7%. So if it went from 100% to whatever the price was, to it increased by 7%, it went to 107%. So the app is now 7% more than the 100%, so it's 107% of the previous value. A foreman earns 12% more than a crew worker. So if a crew worker earned $100, 100% of his wage, the foreman would earn $112. $12 more, 12% more would be, if that's 100, it'd be $12 more. The crew worker earns what percent of the foreman? So we have to divide by the foreman. Well, that's 112. And so the crew worker is $100, and it's an of the, so it's a fraction. So we just have to take this divided by this times 100 to make it a percent. So 100 divided by 112 times 100 would be 82.3%. The next one, of the, so we're just going to compare the two prices. A snowboard sold for 25% less than the marked price. So we have the marked price, original 100, so 25% less, it sold for 75. If it was $100, it would be selling it for 75. The sale price is percent of the marked price. So the marked price has to be in the denominator. The marked price was the $100. The sale price is 75. So 75 divided by 100 is 0.75 times 100 is 75%. Noah's credit card is 5% less than it was last week. His debt was what percent of its current value? So his credit card debt was, let's just say, $100. Then if it's 5% less, it's now 95. Now, which one goes in the denominator? Is what percent of its current amount? So the current amount is 95, and that has to go on the bottom, the denominator. And so we're going to do 100 divided by 95. And then times 100 is 105%. The debt was 105% of its current value. 105.2. 105.3%. Okay? So that's the percentage ones that we did. Now we just got some regular arithmetic to do here, and it says Americans flew 573 billion. So billion is times 10 to 3 would be 1,000, 6 is a million, 9 is a billion. If there were 330 million Americans, how many miles did the average American fly in a month? Well, this is in the whole year. So we got to divide this down to a month worth of flying. So that would be divided by 12. And we get 573. And we can go times 10 to the 9th divided by 12. Or we could have done 573 to enter exponent on 10 of 9 divided by 12, and we get the same answer. So that's 4.775 times 10 to the 10th miles in a month on average. So how much per person? So we got to go 4.775 times 10 to the 10th divided by 330 million. 330 times 10 to a million is not 3, but 6 times you'd have to multiply by to get million. So we want to take our answer divided by 330 EE6. And it's 145. So 145 miles per person per month. Now, I want to show you something here that you may mess up. If you decided to do this 4.775, this answer up here, times 10 to the 10th divided by, and if you tried to type it in this way, you'll get the wrong answer. 330 times 10 to the 6. And we got not 145, but 101.45 times 10 to the 14th. And that's because if you type it in this way, it's going to take this number divided by the 330, which is good, but take that answer times 10 to the 6 and not divided by 10 to the 6. So to get it to divide by all of this, you need to put that in parentheses on any calculator. So 775 times 10 to the 10th divided by parenthesis 330 times 10 to the 6th, close the parenthesis, and now we'll get that 145 that we had before. When you do the E notation, it thinks of that as already in parentheses. If you don't do the E notation, you have to put parentheses around it. Okay. How many significant digits? Well, it's 1, 2, and that 0 counts because it's after a decimal. All zeros after a decimal count. 1, 2, 3, 4. This has 1, 2, 3. This has 1, 2. This is a 0 not after but before a decimal, so it doesn't count. So it's just 4, 9. So there's 2. So on this one, the next decimal place, not the tenths, the hundreds, the thousands, could be 5 more or 5 less and round to this number. So it's going to be plus or minus 0.005. That much more than this could round down to this, or that much less than this number could round up to this. What I'm saying, in case you don't get that, 32.015 could round down to this. This is right on the edge of the borderline. And 32.005 could round up to this. So it's plus or minus 5 in the 0.00, this position, not tenths, hundreds, but the thousands. So to figure the percentage error, I take this divided by the original number. 0.005 divided by 32.01, and I get this times 100, and I find it's 0.02 rounded off. I won't round it off. 0.016% error, because I already multiplied by 100, so I don't want to move it again. Now this one, it would be 0, 0, and the next place could be 5 higher or lower and round to this. So it's 0.005. Looks like it's the same number as there, but you got to remember that this is times 10 to the fifth. So this has to be times 10 to the fifth, because this number is really 8,21000. 1, 2, 3, 4, 5 times we multiply by 10. And so it could be off in this place, which is in the hundreds, ones, tens, hundreds. So it could be 500 more or less. And this times 10 to the fifth moves the decimal 1, 2, 3, 4, 5, making it 500. So the error on this is not 0.005, it's 0.005 times 10 to the fifth. So then to figure out the percentage error, we can take either one of these divided by the original number and get the percentage error if we take it times 100. So if I go 0.005 times 10 to the fifth divided by 8.21 times 10 to the fifth, and now the 10 to the fifths would have canceled, so I could have just done 0.005 divided by 8.21, but I get this number changing to percents by multiplying by 100. I get 0.06%. 0.061%, rounding it off. It's a small percentage. It's less than 1%, less than 1%. But this one's more than that one. This one had less significant digits, so it has more error. This has more significant digits, so it has less error. This one has even less significant digits, so it's going to have the most percentage error. So this is 409, and this could have been plus 490. 495 could round down to 490. 485 could round up. Numbers in between these two round to 490. So we could say this is plus or minus 5, because this 0 isn't a significant digit, so it could have been 5 higher or lower. So if I take 5 divided by 490 and times 100 to get the percent, I get 1.02% error. Percent error. So, which one has the most precision? The most precision is the least error, and so that's A. And which one has the least precision? That's the one with the most error. That's C, with most percentage error. So you got to be able to do the tables correctly to be able to answer these correctly. Calculate the following using the rules of significant digits. So the perimeter. So if we have a rectangle that's 5.301 on this end, it's also 5.301 on this end, and the other way is 12.4, so it's 12.4. Perimeters, all these added up. Or you could take 2 times that plus 2 times that. Or you could add these up, the two of them, and then double the answer. I will do it that way. So I'll go 5.301 plus 12.4 times 2. There's the perimeter in meters. So I've got 5.301 plus 12.4 times 2, and I get a perimeter of 35.402 meters. But when I give my final answer, there are 1, 2, 3, 4 significant digits here, only 3 in this. So I should round this to 3. So here's the third significant digit. This is not bigger than 5, so I don't round up. So I would report 35.4 meters. Now the area. So we got 7.2 length times width times 25.3059. You multiply them, you get the area, and that multiplication comes out to be 182.20248. This had a lot of significant digits, 1, 2, 3, 4, 5, 6, but this only had 2. So it's off by it could be off quite a bit in that place. So we can only keep 2 significant digits. So we'd go 1, 8, and then round that 2 to 0, and the rest of this is gone, and we'd say it's that many feet squared. Okay, a table one. Test positive, do have cancer. This is a correct test. Test positive but don't have cancer, that's a false positive. Test negative but has cancer, that's a false negative. Now it says here, consider population of 5,000. So that's the total. And where 150 have cancer. So have cancer. So if 150 have cancer, you take that away from 5,000, you get 4,850 that won't have cancer. Subtract that from that, you get this. Make a table showing the correct number of people diagnosed. Now it says cancer correctly diagnoses cancer in 92% of the time. Test positive for cancer, 92, so it's 0.92 of the total number that have cancer, which is 150. So it's correctly diagnosing these, so 9.92 for 92% times 150. It gets the 138 correct, which means 138 from 150, it gives false negative on 12 people on average. Okay, and the same test also correctly predicts 94% of those who do not have cancer. Negative tests don't have cancer. So it does this box 94%. So 0.94 times all of those that don't have cancer, which is 4850. 0.94 times 4850. So it gets these 4,559 people correctly diagnosed that don't have cancer. But it does predict the rest of these 4850 minus the 0.4559 that it got correct. There's 291 people it gave a false positive. Said they had cancer, but they really don't. Don't have cancer, but the test suggests they do. So the total number of people that test negative then are 12 plus this. So that's 12 more than 59, 61, 71. 4,571. And the total number of people that test positive, 138, that's 391, 399, 429. So this plus this should equal 5,000. That's all the people. There'll be 429 that test positive, 138 of them have cancer, 291 don't have cancer. There'll be 4,571 that test negative, 12 of them that do have cancer, and 4,559 that don't have cancer. So we've filled out the table, including the false negatives and positives. And now we have to think, what is the chance of someone testing positive? Well, here's all the people that tested positive. So we're comparing to the test positive. And not having cancer. So all the people had tested positive, and there were 291 that didn't have cancer. Change that to 1%, and we get 291 divided by 429 times 100, and we get a 67% chance, 68%, 67.8% chance that they tested positive and don't have cancer. There's a better than 50% chance that they don't have cancer even though they tested positive. Okay? Even with tests that have pretty good percentage rates, a top positive test could still be quite wrong. All right, the back page. So what percent, if 52 out of 170, so 52 divided by 170 is 30.58%, 30.6% rounded off. 16 out of 30, that's 53%. Drug B, 28 divided by 100 times 100 is 28%. And divided by 100 times 100, it's going to be 52%. Now, overall, 52 plus 16 is 68. 68 out of 170 and 30 is 200. So that's going to be 34%. 68 out of 200 is 34 out of 100. You have to divide both those by 2, and that's how I got that. And 52 plus 8 is 60, plus 20 is 80. 80 out of 200. So that's 40%. And I could do 80 divided by 200 times 100, and I get 40. So there's the table filled out. Now, which one says A is better? Well, A does better on men. A does better on women. So A is better for men according to the data and for women according to the data. Men is 30.6 to 28. Women is 53 to 52. So looks like A is the best drug. Unless you look overall, and it is 40 to 34. B is better overall, 40 to 32, 34, 40 to 34. And that's that test.